Okay, so in this video, we're going to just finish off proving Abel's theorem by showing how we can use the proof that we just did, the fact that we just proved, we can easily derive the truth of Abel's theorem in the general case from that special case, okay? So, so we kind of do this in steps. So first, okay, hold on, let me, so generalizing the special case from previous video. First we're gonna try to take away the assumption we made that f of 1 equals 0, right? So first, suppose f of x equals n x to the n from n equals 0 to infinity, and that this has radius of convergence r equals 1, and that that the series converges at x equals 1, but not necessarily that it converges to 0. Okay, so we're just assuming that the series converges at x equals 1. So then the previous proof, so then if we just define G on, G on the domain of f by g of x equals f of x minus f of 1, then G, actually, better yet, instead of f of x, let's just write the series again. It's good to kind of even though f of x is the series, it's better to refer to the series just by itself when possible, because a function technically convergence and uniform convergence and stuff, those are properties that we ascribe to the series, but not necessarily the function. You can say f converges if you want. It's just, I think it's a little bit more kosher to say that the series converges or something. So, and then define that this one minus, minus the sum from n equals 0 to infinity of an. Okay. So then, so this is just some constant, right? So, so then G satisfies the assumptions of the previous argument. So G is continuous at x equals 1. But then, since f of x equals g of x plus f of 1 on the domain of f, we have that f is also continuous at x equals 1. Okay, very simple. Honestly, I probably didn't have to make such a to-do about it, but I decided I wanted to really lay this out very carefully for you guys. So what this allows us to do now is for any series, any power series with radius of convergence 1, if it converges at x equals 1, then we know it's continuous there. Okay, regardless of what the value is. So let's see. So, right, okay. Then next, suppose f of x is a power series from n equals 0 to infinity with radius of convergence r, positive number, finite positive number, okay? And the series n equals 0 to infinity converges at x equals r. Then define g of x to be the series an r to the n, x to the n, from n equals 0 to infinity. Then g of x equals f of rx, right? So, well, better yet, so then the radius of convergence of this series is 1 now, right? Because if you do the root test on this, the nth roots of an are supposed to converge to 1 over r, right? Or rather, the lim sup of it is 1 over r, and then the nth roots of an to the an r to the n would be 1, right? So so the radius of convergence of this is 1, and it converges. So by it, I mean the same series here. This series converges at x equals 1. So by the previous proof, this series converges. So the series an r to the n, x to the n, from n equals 0 to infinity converges uniformly on 0, 1. So g is continuous at, x equals 1. Since f of x equals g of rx, g of x equals f of rx. So f of x is g of x over r. So g of x over r for, well, on the domain of f, right? F is also continuous at x equals r. Okay? So now we've just shown that basically any power series that converges at the right endpoint of its interval of convergence is continuous at the right endpoint. So now we just have to show that this is true for the left endpoints too. But this is just, now we can just use like a sort of a mirror argument. So, or not a mirror argument, but there's like a simple symmetry. So now, suppose f of x is the sum of an x to the n from n equals 0 to infinity with radius of convergence r, and this series from n equals 0 to infinity an x to the n converges at x equals negative r. Okay, so then define g of x equals the series from n equals 0 to infinity an negative x to the n. Okay, then the radius of convergence of the series for g is also r, and this series converges at x equals, so we literally just like reflected f across like the y-axis basically, right? This series converges at x equals r now, So the preceding arguments show that G is continuous at x equals R, since f of x equals g of negative x, this means f of x, well, f is continuous at x equals negative r. Okay, so all in all, that completes the proof of Abel's theorem, because we've now shown that for an arbitrary power series with an arbitrary radius of convergence, if it converges at either one of the endpoints, then, to whatever value, we don't care. If it just converges at all at either one of the endpoints, then it's automatically continuous there. Okay, so that's Abel's theorem, and so that does it for the analysis of continuity of power series. So then in the next 2, maybe 3 videos, I'm gonna just cover these things about integrating and differentiating power series.